Hello, my name is Lukas Landgraf, and today I'm presenting memory efficient scheduling of query pipeline execution. This is a project done in cooperation with SAP and the Technical University of Dresden. In database cloud scenarios, we want to upscale service quality while reducing cost. And regarding in-memory DBS, which are used in clouds, a huge TCO contributor is main memory. And main memory consumption should thus be kept minimal. And regarding in-memory DBS, there are two kinds of main memory cost contributors. So there is raw data storage for base data, and there's also main memory used for query processing. And if we focus on query processing main memory consumption, there are several techniques which we can use to optimize for minimizing it. For example, we could use memory efficient operator implementations, we could use compression for intermediates, and we could also leverage buffer pool management in order to spill database pages to disk. However, what if we found another approach that would be feasible for reducing main memory consumption in memory DBS? And that would be pipeline execution orders. How does it work? Well, first off, we are presented with a QAP using this running example originating from 5 base tables. And we have several assumptions here. So we have non-cardinality estimates noted on the sides of the edges of the query execution plan. And we have fixed probe and build sites if we consider only using hash joins for our hash join implementations. And since we in modern in modern query processes only use pipelines, we use some pipeline execution model to draw continuous edges along the probe sides of a query execution plan. For instance, we can draw this edge from R to the result, and one edge from S to the join with R, and so on and so forth. Now, if we now try to transfer this into a pipeline view of a QEP, where we have pipelines, and at the end of each pipeline we have pipeline breakers, which can either be hash tables in order to facilitate a hash join with a subsequent pipeline, or pipeline breakers which are result buffers. And inside those pipeline breakers you will have a memory cost noted as the number. And we use this bow tie notation to note that some pipeline uses, for instance, pipeline U uses the pipeline breaker of V in order to execute some hash join. Now, we also name the pipelines after their origin base tables for later introduction of our algorithms. And also we argue that the memory consumption of the pipelines is actually dominated by their individual pipeline breakers. Also, we also assume that we execute at most only one pipeline at a time. And resulting from this, we have several dependencies between the individual pipelines. For example, S can only be executed if T has already been executed, and U can only be executed if V has been executed, and R can only be executed if S and U have been executed. And up to those constraints, there's a certain freedom of choice of which pipelines to execute one after another. Now, where's the potential for memory savings? Well, again, we are presented with a pipeline view, and we try to construct a new kind of diagram where we model the memory consumers along the y-axis and the lifetime of the consumers on the x-axis. And we do this for 2 different PEOs. For instance, we have now PEOs, one PEO1 and one PEO2, and which result in the following resource chart, where on the side we have the memory consumers on the y-axis and their lifetimes on the x-axis. Now we choose to execute V first when we execute T, then we execute U, S, then we execute U, then we execute R. And then we choose to execute, for the second PEO, we first choose to execute V, then we execute U, then we execute T, when we execute S, and then we execute R. And those different orders always produce the same result tuples in execution, and query execution time performance should also be equal. But there is an opportunity for different memory consumption profiles. How does it work? Well, again, we try to project the profiles of the memory consumptions down as the memory consumption over time for both PEOs. And the area under the graph we shall call the memory integral, which we actually want to minimize. Now, if we overlay those two memory profiles, we can see that there's indeed a difference between the memory integrals of the two different PEOs. And this should be minimized. So how do we position this in query processing? When do we optimize? Well, first off, we start with a query. And then we put the query into query optimizer, when we obtain a query execution plan, and then the query execution plan is fixed. And right after we obtain the query execution plan, we plug in our PEO optimizer. And then we use the PEO output by the PEO optimizer for actual query execution. And in the end, we obtain the result. And regarding the PEO optimizer, in the paper, we present different scheduling algorithms for systematically finding good or near optimal or optimal pipeline execution orders with regards to memory consumption. And we have two kinds of algorithms for this. We have optimal algorithms, which always find the best possible PEO with regards to memory consumption, and we have heuristics. We have one exhaustive search implemented, which enumerates all possible alternatives of PEOs. Then we have branch and bound search, which relies on candidate pruning. And regarding heuristics, we have one pure heuristic, which only finds one particular PEO according to some principle. And then we have feta skip search, which also relies on candidate pruning. Now, we have several goals that we want to show with our approach. First off, we want to show that there are indeed savings in real-world systems that we can obtain. And we want to show that there's a cost model quality, so there's a correlation between the estimated memory consumption savings and the real savings. We want to show that there's a low PEO optimization overhead, and we want to show that there is minimal query execution time impact. And due to the lack of time, we cannot explain all algorithms in detail, and so we will focus on one particular aspect of the algorithms, which is the cost model. Again, we start with a pipeline view of a QEP. Then we take one possible PEO as a starting point in order to deduce our memory costs. And the memory cost that we will face is actually the memory integral of a PEO, which is the sum of all memory used over time. And we defer the memory size of the individual breakers, which are the consumers of memory in our model, to be the cardinality times the row size of the intermediates inside the pipeline breaker. The lifetime of a pipeline breaker is the sum of pipeline execution times, which is estimated as the pipeline execution cost. And the pipeline execution costs themselves are the cost of the individual subtree. For instance, we have pipeline R here, which covers the entire subtree. And we take for instance, the out costs for this, and then we subtract all the build side subtree costs. So in this particular instance, this would be the ST subtree costs and the UV subtree costs. And then we would add additional writing costs. With the cost model as the foundation for our algorithms explained, we will now go to the evaluation. Regarding the systems that we use the pipeline execution engine prototype, which was also the finalist of the Sigma 2018 programming contest, and we use a single-threaded PEO enumeration for all algorithms. The benchmark in our instance is the join order benchmark, and we considered only the indicated queries, and all the queries are our query plans are stripped of non-join operators due to constraints of the prototype. And we consider four kinds of data sets. We have the unmodified join order benchmark data set. We have the SF2 data set where the AK name column is scaled with a scale factor of 2. We have the 4 data set accordingly, and the AK name SF4 company name SF8 data set. And we use those latter 3 data sets in order to introduce higher skew. Regarding the PEO enumeration cost model parameters, we set Cout for as our cost model for QEP enumeration and also for the calculation of the execution costs of the pipelines. Now, regarding the experiments that we wanted to execute, we first wanted to show the memory cost optimization potential in order to see that there are real savings that we can obtain in real-world systems according to estimation. So first off, we will plot the estimated memory integral of the individual PEOs. And for this, we will now focus on query 9 of the joint knowledge benchmark with the SF4 dataset. And each of the graph otherwise represents also one query with one particular data set. And if we now focus on this particular example here, we will first have the memory integral of the worst PEOs taken as 100%, and the y-axis on the bottom actually starts at 80% of the PEO, and on the y-axis you will always have the estimated memory integral. Now, what you can observe is that for the query 9 with the SF4 dataset, we have a possible optimization potential of 11.1%. And what you can also obtain from this graph is that the heuristics found a PEO which was very, very close to the optimum, but not the optimum. And due to this, we can first off say, okay, there are savings within the exhaustive approach, and also our heuristic also found a PEO which was near to the global optimum, and there are improvements in memory consumption of up to 11.1% in the joint knowledge benchmark scenario. So we can check that. Regarding the cost model quality, we first want to establish the correlation of the estimated and the real memory cost. And for this, we will plot the memory cost of all PEOs for query 9 of the joint knowledge benchmark. First off, we measure the pipeline execution times and average those to actually defer the measured memory integral. And within this diagram, each dot represents one particular PEO, and on the x-axis you will have the estimated memory integral, and the y-axis you will have the real memory integral. And on the bottom left corner you can see that they are the best possible PEOs, so they have a minimal memory integral, and on the upper right corner you can see the worst possible PEOs. And as you can see, there's already quite a visual correlation here. And actually the correlation coefficient up to the Pearson method is 0.94. And this indicates that there is indeed a clear correlation between the estimated and the real memory integral. So we can check that also. Now, regarding the low PEO optimization overhead, we wanted to measure the PEO enumeration overhead before the execution of the individual queries. So we evaluated our 4 algorithms regarding their enumeration overhead times, and we can see first for the exhaustive search that we start for low complexity query execution plans with double-digit microseconds, and this goes up to 302 milliseconds in the query 33, which is due to the high complexity of the enumeration algorithm. And if we now compare this to the longest path heuristic, which only considers one particular PEO, but also is most of the time very close to the optimum, we only also have double-digit microseconds for low complexity queries, but in query 33, we have an enumeration overhead which is 4 orders of magnitude smaller than the enumeration overhead of query 33. And the other 2 algorithms, so theta skip search, which is also heuristic, and branch and bound search, pose a certain balancing between those first 2 approaches. So again, we can see that the longest path heuristic has a negligible runtime overhead, and it should indeed be a very feasible approach to optimize for main memory consumption. Other algorithms pose a trade-off for this regard. And regarding minimal query execution time impact, we measured the average query execution times over all possible PEOs as an average, and then put the PEO query execution times relative to this. And we measured end-to-end runtimes in this particular instance. And for query 9, which also showed the largest improvements regarding memory integral, we can see first that there is no correlation between the PEO and any kind of measured actual runtime, and also what you can obtain from create, that there is indeed jitter, but that jitter is induced by the enumeration overhead of the query. So runtime overhead does not depend on the PEO, and the deviation is caused by the enumeration overhead of the PEO optimization algorithms. So we can also check that there's minimal query execution time impact. Now we go to our conclusion. Our work found that PEOs have an impact on memory consumption. We formalized the problem, and we also provided position and query processing and provided 4 algorithms for systematically finding optimal PEOs. And furthermore, we evaluated experimentally that there are indeed savings to obtain, that there's a correlation between the estimate and the real world values. We showed that there is an insignificant impact on query execution times, and also we showed that the enumeration overhead is negligible if we only consider certain algorithms for high complexity queries. I thank you for your attention, and I would now be open to questions.